All right, so we're starting here with Pranav's choice, series of the day. So this is B. And here's the thing. Immediately here, I see the -1, but let's see what the chart is going to tell you to do here, the magical chart. Check for absolute convergence first. So what do I need to do here, Pranav, to check for absolute convergence on this series?
Take the absolute value of the function, so you just have 1 to the power of n over ln n.
Okay, so this guy now. So pay close attention. I can already tingle like on what the test that's going to work is. You should be a little bit too tingling already, but let's pay close attention. I will get there. Is A of n referring again to this bit? Sorry, because the text boxes don't behave well with the writing. So this bit over here is an. Is it raised to some weird power? Yes or no? Just yell it out.
No.
No. Does it look like a P series?
No.
No. That would be 1 over n to some power. Is the limit easy to evaluate? I'd say yes. Just plug infinity in here. What do you get?
0.
0. So we got 0. See, we did the limit. We got 0. Okay, so we're moving again to the right. We're not going down. So we basically did quickly the divergence test here, and we saw that it doesn't diverge. Is it a product of these weird things here, brackets of n or factorials?
No.
No. Okay. Is it integratable? That's debatable. Again, 1 over ln to the n. 1 over ln n. Maybe if you do like integration by parts, maybe. So I don't want to go there. I probably don't want to go there right now because that seems like a lot of work. So that's why I say maybe. Keep moving to the right. Okay. So what is your hunch? Like your guess over here? Does it converge or diverge? Look at it. What's your hunch?
Diverge.
Okay. Anybody want to, again, add, because this is a discussion. I'm going to make it fun tonight. I'm not going to be the only one talking. So what do you girls think? Kelly, Grace?
Diverge.
Diverge. Grace, you think the same?
Would it converge if 1 over ln n just keeps on getting smaller?
We just did the limit right here. We do get that the series, the last term of it is going to go to 0, but that doesn't mean that the series will converge, right? Not because the sequence converges, we're going to say that the series, because the series is a sum. The sequence is a different thing, but the series is a sum. It keeps summing those previous terms. And it doesn't matter that the last guy is 0. Maybe the guys in the middle added up to something huge, right? Maybe if they added to something that's already infinite, that it doesn't matter that we keep decreasing the inputs, right?
Okay.
Okay. So you'd say diverges, converges?
So diverges.
I'll follow you on that. Okay. And I'll say it also diverges. So what does it say to do here? Can you come up with another series that is smaller than this? So let's think 1 sec. Okay. Let's say right now that n is equal to 2. Okay. 1 over ln of 2. I'll put it in my calculator because that's a weird number. 1 over ln of 2 is like 1.44. Do you think you can come up with something else here that you can substitute for that? It'll give us a smaller number right now. Trust me, it's easier than you think, this one. Okay, if you're having trouble with that, first come up with something that is simpler than this, but looks pretty much identical to this. Some function that is similar to this, but, behaves again we're going to check to see if it behaves, if it's smaller. What looks similar to this and is simpler to work with? Anybody that has an idea, yell it out.
1 over n.
1 over n. Okay. So she's saying 1 over n. If I plug n equals 2 to 1 over n, Kelly, what do I get back?
1 over 2.
4.5, right?
Yeah.
So which one of these is bigger?
1 over ln 2.
Absolutely. So that was the 1 over ln n here. And this is the 1 over n here. Now, you'll say, I'm not convinced, right? I'm not convinced. I would like more. Yeah, you can do more. I encourage you to do more points to make sure that this holds for all n, right? That I didn't just pick an n here that just works. So let's try, because I'm not convinced, let's try 1,000. So 1 over ln of 1,000 is about 1, let's see here, 1 over ln 1,000 is around 0.144, I guess. Yeah, I'm not going to keep more like this. Okay, versus 1 over 1,000, you can tell me, you don't have to use your calculator, but it is 0.001. Who's smaller again? Which of the two numbers, the right or the left? Who's smaller? We can compare numbers, right? Right? I know you've lost yourselves in integration and all that, but we can compare two numbers still, right? This one's smaller, way smaller, okay? So we're keeping the ball going, you see? Smaller. And again, you can try any number that you want, but I'm pretty convinced right now that you all picked a series that is smaller. I'm convinced. So, okay. So this is your AN, this is your BN. Anybody want to have a word about what BN does? BN here, okay, is now this series. And again, we'll start it at 2 like the other one did. So you're checking. What are you checking to see? Let's see. You were on this step. Can you come up with a BN that is smaller? Yeah, we did. Does your BN diverge? Look at it. Look at it. Look at it. You're analyzing this one. What do you know about this one? By the way, this is the harmonic series, if for people that don't know. I just noticed Kelly's gone, but don't worry, we'll give her the recording. What do you know about the harmonic series? Converges or diverges?
Diverges.
And it is because, again, if you ran this through the tests here, you'd stop here because this is a P series, okay? And the P value is 1. So if we go down here, is P greater than 1? No. Was the original series alternating? No. Divergent. So again, we conclude that this little bn here is indeed diverging. Okay. So by P series test, again, I'm going to say here diverges by P series test. Okay. Therefore, thus, AN also diverges, but not by the P series test, by the comparison test. That's what we did right now. We compared it to another series that is smaller, and we saw that the smaller series diverges. Therefore, the larger series will diverge as well. That's your work, and you are done. Okay, I'll put that back there. So it was the comparison test that we needed to do. I don't know how I'm going to isolate the writing now from this. This is going to be interesting. I'm going to do that. I'll fix that, don't worry. It's just the way the cookie crumbles with OneNote. Okay, so we'll put the example down here and we'll take that away. Okay, so that's Pranav's example done. I'll just bring the work up there. It wasn't a lot of work, right? You just have to take that path on the sheet and see again what you need to do. We needed to do the comparison test here. Questions before I move on? Moving on. Leah, you're the next victim here. You need to pick one. So we did B. Let me know.
1D.
Okay, going to the ones that are difficult. Let's see if I can handle them too, right? Some of them are a little too difficult sometimes. So we've got -1 to the n, 2 plus, what is going on over here? 2 plus 1, -1 to the n, divided by 2 to the n. Okay. All right, that's 1D. I swear, sometimes you guys are trying to punish me by doing these. I swear. Okay, so again, we start rolling the dice here forwards, go back up. So working a little bit with Leah. What's my first thing that I need to do here, Leah?
Check for absolute convergence.
Okay, so I'm thinking right now how to deal with the inner -1. So it says 2 plus that. And I'm thinking a little bit how to deal with that guy. So it's fine if we go and check right now just the positive version of this series. I was thinking of actually splitting it into 2 and checking the individual bits if they converge or not. Because if you split it into 2 bits and one of them actually diverges, you're screwed. You're going to diverge as the sum. But if both pieces converge, then you can rest assured that, you know, the entire thing will converge. I'm just thinking right now, how should we treat this? Because this is an odd one. Give me a sec as I pause the recording. So I'm feeling the idea here of splitting it up again into 2 bits by distributing this into here. First bit becomes 2 times -1 to the n over 2n. And the second bit, you take these two, you can think of them as legitimately just being x, the -1 just being x. And when you merge the 2 brackets, you raise the whole bracket by an amount. So you have here actually n plus n. I need to be careful about that. Okay, so this is the series opened up into 2 bits, and then the bottom, I can write this as 2n. Looks good to me. So from here, what I can do next is I can check this bit by bit. So let's do that. I'm going to bring in the first one around. Leah, what should I do?
Check for absolute convergence.
How
Like
do I
take
do that?
absolute value of it.
Okay. So again, this is what we're checking. All right. And again, I don't need to take the absolute value here at the bottom. You'll see me sometimes skip that because these terms are all positive. There's no way you can make this into a negative right now, no matter what n value you put in. So I don't need any absolute values in there. Okay. Is a sub n raised to some weird power of n? Actually, 1 second. You know what? I'll give you a major hint here, Leah. Okay? I'll give you a major hint. Take a look how I can write this so we can skip some steps. What do you think about this? I'll help again over here a little bit. Reminds you of anything here with this guy, the geometric series?
It's a geometric series.
It is. Our A value right now is 1. Our R value is 1/2. And we have here basically n minus 1 exactly. Okay. And if so, is that R less than 1? So for us, I'm just going to go back and show you into the notes again. Final. Okay. So this is a geometric series. All right. And what values does it have for R and A? Well, A here is just 1. R is 1/2, and it is less than 1. And I can take the absolute value of it. It doesn't really matter, but it is less than 1, that R value that we have here. So what does it say here, Leah, on our geometric series test? What are we being told? If it is less than 1, then what? Do we converge?
We don't diverge.
We do converge, though, to this value. That's a finite value. So this guy is right now convergent. Whoops, wrong file. So because, again, this is less than 1, convergent. Maybe that's the one thing I haven't added on my little sheet here. I have not added geometric series because I haven't encountered one. But, you know, first time for everything. So that's what's going on over here. You started with this. You're checking again. What we're doing here is just taking the absolute value. And then we're checking to see what we get. And we got a geometric series. So once we get the geometric series in, we ask, what are these values? And we saw very well that the R is much less than 1. So this is convergent. And because we were checking for absolute convergence, it's not just convergent, it is absolutely convergent. So the first piece, absolutely convergent. What about the second piece? It looks to me like it's going to be the same story again here, Leah. Okay, if we take a look at it and we check for the absolute convergence again. So again, we decided to check piece by piece. You see that we're checking again 1/2n instead, and it's the same kind of deal. It's another geometric series, okay? That I will say here again. This can be written like this. All right, it's another geometric series. And it converges because of the same reasons. A is 1. R is less, absolute value of R is less than 1/2. Therefore, absolutely converges. Okay, so if you have the sum of two absolutely convergent stuff, sum of two absolutely convergent series is an absolutely convergent series. Is an absolutely convergent series. How would that make sense, right? No matter how big of a number these things converge to, the thing is that they both converge to a finite number. Two finite numbers, if you take their sum, they will always give you another finite number and not infinity. So that one is convergent. I'll put the work here that we did. We didn't really go through the chart because it was a unique one. but I was aware, I saw the form and I was aware that this is this is a geometric series. All right, so we did it piece by piece. Grace, get ready because you're picking the next one. All right. So that one's done. Where do I go next?
Can we do M?
M or N?
M.
M, okay. Girls really like torturing me, huh? Okay. I've noted that. I'll remember when I'm rounding the price for the tutoring. Do not worry. I'm just kidding. Okay, so this one over here, this looks like if it was a limit, oh my God, actually it might be a test that it requires a limit here. And if we need to take the limit of this, this is rationalization. I don't know, it's giving me some Math 127 vibes right now because we're reviewing there too. And that's a rationalization if we were taking the limit of this. Will we though? I don't know. We'll have to see, Grace. We'll have to see what's up here. So let's take that upstairs to give it the treatment. Okay. First things first, what to do here, Grace?
Check absolute convergence.
All right. So again, my first move every time. Now, here's the thing. If we don't get this to absolutely converge, then we need to go back and do the alternating series test. The thing though is that you would have checked for that absolute convergence anyways at the very end of the problem. So I'm kind of doing things in reverse than what your regular prof might do. It depends on how he sees things too. But I think it's more efficient to do the absolute convergence first. And if we see that it converges over there, we know immediately it's absolutely convergent, moving on. But if we did not do it first, the problem is that you could converge, this series here could pass the alternating series test, and then it will fail the absolute convergence. I don't know. It depends how you want to start, but I recommend it's a good habit to just start with this. It always, I think, saves time at the end of the day. Not a lot, but enough so that I like it more. Okay, so we start from checking this out, and we got to check out what does this thing do. Okay, so we're going to run this guy through over here, our tests or our questions. Grace, is the whole thing raised to some weird power of n?
No.
No. By the way, this question is for you to check out if you need to use the root test, because this test is really rare, really rare. Like, I can't even see one here that you might use that on. It's a very rare test, okay? So let's get that out of the way, the root test. And that's why, again, I move on after that. Okay, sadly, I can't carry this with me. The text here, the text boxes are annoying. Okay, is it a P series? I'll just make it small.
No.
No. Okay, keep moving it through. Maybe move that away a little bit. Is the limit easy to find? I'll answer this one again for this time. I'd say kind of, okay? And I really have a strong feeling that this limit is non-zero. Really have a strong feeling, because look at this. Why is George having tingles? Because the largest power inside that square root is n right now. Like, I mean, if you think about it. If you square root the n squared, you get n. That's the largest power that you have over here on this part of the equation. And then you have another negative here, n. You might say that should give you 0. Not quite. It should give you a finite number. Maybe it's 0, but I'm telling you, this is going to be a finite number. It's not going to be infinity. So we're betting against ourselves here. Is that finite number going to be more than 0 or 0? I don't know. I feel like taking chances here, Grace, but if you wanted, you could have always went through over here and continued the roll, but I really have a hunch that it's going to fail the divergence test. I don't know why, because of this, because of the n minus n situation. So if you trust me on that journey, I might end up being a fool, but I have to do something since I'm the tutor. So where I'm going to go with this immediately is the divergence test right now. And so I am going to ask, what is, and Grace, you're going to help me out here a little bit. What is this limit here? Let's start it out. So to evaluate this bad boy, I said I'm going to do rationalization. Now, rationalization takes advantage of this situation. Difference of squares, basically. So right now you have this. What should I multiply it by to induce a difference of squares, Grace?
Root n squared minus 2n.
You're close.
Oh, root n squared plus 2n plus n.
Plus n, okay. So I'm gonna do the ratio here like this. I'm doing a ratio because, again, I want to basically multiply this whole thing by 1 because this didn't exist here before. And now in our next step, we have opened up here these. What are they going to be, Grace? Think about it as I'm writing the denominator.
Oh, okay, yeah. N squared plus 2n minus n squared.
Mm-hmm. And what do we notice? The n squares go away. That's a completely different limit right now.
Mhm.
So how do we solve this kind of limit typically? This is a polynomial now to my eyes. And since it's an infinite limit, usually I like to pull the largest power of n, like factor it out of the things that I have here. I already see the answer, but again, I want us to do, because we have to show work if we're writing the exam. So let's see here, Grace. What is the largest power of n on both numerator and denominator?
N.
People are going to be like, what do you mean? There's an n squared there. No, it's getting square rooted. So the largest power is actually n on all the terms. So we're going to factor out that n right now. It's going to have n over n. And Grace here, what am I going to be left in the numerator and denominator?
In the numerator, it's 2. In the denominator, it would be plus 1 after the square root.
Now, to help you out a little bit, it's like you have factored n squared out of the square root.
Okay, so you get 1 plus 2 over n.
Perfect. So what do we get here? These cancel. And when you plug in the infinity on this one, this goes to 0. What do you see for the limit right now?
It's 1.
Close. You have basically 2 over square root of 1 plus 1. Oh, you meant the overall limit. Sorry.
Yeah.
I was just looking at the denominator. But yes, everybody else, this here just ends up being 1, which is not equal to 0, which means this diverges by the divergence test. Okay, I am not a magician coming up with, because I know a lot of you would have passed here and you would have said, yeah, it's not easy to find the limit. Let me tell you why I had a hunch. It's really ridiculous if I tell you the reason for my end. It's not because I'm clever. It's because this thing is on limit questions all the goddamn time. Let me show you over here how bad it is. Like I can just go to a limit here. Where are the limits actually? I'm blind. There. Okay. So I can just go to a limit. Look, first thing we hit something exactly like this. And I'll prove it further. Here it is again. Here's the exact same thing that you just did. I think that was N, or maybe it is the exact same thing. I don't know. I'm not switching the folders right now, but there it is. And I'm telling you, it's all over 117's limits. And this one is dealt with rationalization. So my brain as the tutor, I picked it up and I'm like, this is really sus right now. Why would they put that there if they don't want you to use the divergence test? I was like, kind of like unsettled because I know this isn't a lot of limit questions. So I'm like, why would they put that there right now, making it so obvious? It is the exact same thing, by the way. Why would they put that there if they wanted me to not do such a limit? So that's what got me stuck there. Anyways, it completely failed, but it has still hope. Hold on. We were checking the absolute convergence, right? So this is not absolutely convergent by divergence test, okay? That's fine. That's fine. We're still hanging out though, because remember, you are following the branch here. Let's see what the branch says. Use the diagram a little bit too. Is the limit easy? Yes. Was it 0 or non-zero? It was non-zero, it was 1. Was the original series alternating? Yes. So I'm not done yet. I gotta do this pane. I'll copy it if you don't remember the rules. Okay, so we gotta check now if it actually diverges. Fair enough. So we bring this back in. This is, again, we can label these, but you get that this is check for absolute convergence first. And then we would have stopped if it was converging here, but it's not. So we go further and we check here for divergence now. Or conditional convergence. We'll see which one we get. Okay, this already looks bad that it's going to diverge, but whatever. We'll have to be again showing our work. So here it is. We're going to run the alternating series test. That's the only thing that works on this right now. So we want the function to be decreasing and having a limit of as n goes to infinity going to 0. We can cheat here. We can really cheat here. Hold on. I'll show you how. This is an, by the way, for an alternating series. Again, an is this bit. So one of the conditions says is the limit as n goes to infinity of an equal to 0. Grace, what do you have to say about that? Is the limit of this as n goes to infinity going to 0?
Doesn't it go to 1?
You've done it previously. Look. So I would highlight here, if I was, again, writing this as an exam, I would communicate the fact that I'm not going to retake the entire limit. I'm not dumb. Just going to highlight that and be like, hey, check this out. Okay, I've done the work. So the limit as n goes to infinity is equal to 1, which is not equal to 0. So immediately diverges. I don't have to check the other condition. Diverges by alternating series test. Okay. So watch this. Now you'll say, George, you made us do all this work for the absolute convergence. What were you thinking, right? We could have done this and be done. Are you sure about that? Because you would have needed to do the same limit again here, okay? So even though it ended up that we did the longer way, you would have needed to do this limit anyways. It just so happened. It's coincidence, by the way. So no loss overall. You literally would have done this and saved no steps. So there you have it. Okay, you picked a good one, Grace. I like this one. What do the rest think? Are we all following along? What happened? Because this was a little bit messy. Silence. Okay. I guess here we're all okay. I don't hear yelling on the mic. Natalie, your turn. Your turn to pick, so you can tell us in chat. Hopefully Natalie is here and can hear me. 1L. 1L. Okay. Whoa, what's going on over there? Okay. I just noticed that. Lon. Okay. So the sum from n equals 3 to infinity, 1 over n ln of n, square root. Don't let the function scare you, because again, you might be taking their limit and very quickly conclude that this diverges or whatever. Also, I should note in this recording how much I despise series tests. Like I hate this chapter with all my passion. Okay, it is the worst because you're always on the spot as the tutor, right? I have to guess sometimes, and if I guess wrong, you're all gonna hate me. But even the tutor has to kind of guess it. Sometimes, some other times it's more obvious to the tutor. You know, experience is in the eye of the beholder, I guess. So because I've done a lot of these, I can see some stuff better, but I have to guess sometimes too, just like you. So this is crazy already. N times ln n times the square root of ln. Wonderful. Okay, my hunch. This is a stupid looking function. Whoever made it is intentionally trying to do something here, trying to point you to something. Let me see it. Let me just see it for a second. Give me a minute here, or 30 seconds, just to see it. Pause the recording. Okay, so we're about to check for absolute convergence. And I'm checking again if the smallest n value of that series will give us a negative term, and it didn't. I plugged it in the calculator, it gave us a nice positive. If the lowest value of n doesn't give you here a negative, there's no way that n equals 4, n equals 5, or n equals 10, if you plug them to these functions that all increase, become more positive with larger n, there's no way you're gonna make this negative. You can check if you don't believe again in your own time. How would you know ln of ln n gives a positive without a calculator? That's a good question. I don't think I would. Oh, but I think I could make it happen though here. I'll give you a hint. Ln of ln. Okay. How would you know if it's positive without a calculator? What's ln other than log base e? We're forgetting that sometimes. So if that's the case, then when I put in right now 3, and I look down here, that is 2.71. And 3 is a little bit bigger than this, which means we got to raise 2.71 to a power slightly bigger than 1, maybe like 1.2. I don't know, I'm just guessing. I can use the calculator to tell you exactly, but I'm guessing. The calculator says 1.1, 1.09. So how I look at it, Natalie, I look over here. This 3 is bigger than my base. So right now, this number is definitely going to be bigger than 1. Guaranteed bigger than 1. If it's bigger than 1 right now, then taking the logarithm, again, of a number bigger than 1 will yield you a number bigger than 0. Think about it, because ln of 1 is 0. I mean, I don't have to put in a calculator. So if we have a number right now that we produce that is greater than 1, it means the output overall is going to be greater than 0. And I just prove you that this here, the inside of the square root, is greater than 0. Since we're square rooting something greater than 0, we get something greater than 0. And that's what I did in my brain to prove that this is greater than 0 right now. But I did it with numbers, I gotta admit. I used my calculator. I didn't do it without a calculator. But I know why you're stressed, because you can't use calculators on the final. Fair enough. So you can do with or without, as you see, Natalie. Exactly. She even said to the rest of you, since we aren't allowed calculators. Okay. Obviously here, ln of n, I just proved to you that it's going to be greater than 1. Ln of 3 is going to be greater than 1. That's cool. That's positive. And then n here is just 3. So everybody in the denominator for n equals 3, they're all positive. Guaranteed then, the first term, positive, greater than 0, the first term. There's no way if you use the lowest value of n right now and you got a positive, that you're going to bring the n up and somehow you're going to get a negative. No way. You're just making now the denominator more and more positive as you increase the values of n. That's all that's going to happen. Again, I invite you to use your, if you don't believe me, use your calculator later and plug in 3, 4, 5, 6 for n and see what happens. The denominator will just grow. So you need a little bit of that intuition, right? Like how different values of n affect. Didn't I tell you, I started the, I swear to God, I started the recording and I was like, pay attention to this guy because he's going to tell you if all of the terms in your series are positive. Here we're doing it again. I'm checking the bottom guy to see if the very first term is positive, and if so, and all of these functions grow with n, then everybody is going to continue being positive for all values of n. We're good. No absolute value needed. Good discussion though on that. Hopefully it helps. How to judge again if a logarithm is greater than 1 or greater than a certain value. Okay, so we're good. We don't need to take the absolute value of this. We can just move it through. Now, Natalie, again, yes or no over here. So is this raised to a weird power of n? The whole thing raised again brackets to weird power of n? What do we think? No. Okay, is this a P series? No. Okay. Is the limit as n goes to infinity easy to find? Careful what you answer. Careful what you answer here. Yes or no? Is this limit easy or not? Try it in your brain. Slam infinity into the position of n right now for all of these. If you blow up the n to infinity in the denominator right now, what happens if you just put infinity for all these n's here? What are you going to get? This ln here is going to blow up to infinity. And taking the ln of infinity is going to be infinity. Square root of infinity is infinity. Ln of infinity is infinity. You're multiplying infinity by infinity, which is infinity. And you're multiplying again infinity. So it's 1 over infinity that you're going to get, or 0. So you did the limit. And you got 0, so you're moving again to the right. It wasn't conclusive. The divergence test was inconclusive. Is it a product of factorials or weird bracketed powers of n? No. Okay, again, you need to think of the next one a little bit. Please think about it before you answer. Is it integratable? Can you all think? I want you to help her out, figure this out. What does the rest think over here? Is this integratable or not? I know what you're thinking. I'm crazy for even thinking about it, but am I really? What do you think? While Natalie is thinking, I want to ask Pranav. Pranav, when you see disgusting functions in integrals, usually what's the method that has to be used? Let me give you again, since I have these handy. Since I have them handy, why not? So I want you to look, for example, here. But you see, we have disgusting functions over here, right? What method gets rid of the disgusting function sometimes?
Integration by substitution.
And to judge if U sub is going to work, I'm just refreshing your integration skills a little bit. To judge if U sub is going to work, what do you need to do here? You need to think. Yeah, I'm going to show you this step here. You need to think 1 sec. Is the derivative of the disgusting function off by a constant? We can allow constants. Like, for example, if you had a 3 here or 6 dividing it, it doesn't matter. But the main course, the main dish, okay, is the derivative of the disgusting bit inside our integral right now. What do you think? In this one in particular. Pranav still.
Wait, sorry, you cut off at the last bit for me.
Okay, so we're looking to see, Pranav, if we're to use U sub, if the disgusting function's derivative is in the integral. Is it? What's the derivative of tangent?
Secant squared x.
So that's when I know I have to do U sub here. Okay, bringing it back to Natalie. So let's see over here, Natalie. Tell me here, Natalie, what's the disgusting bit? The left or the right? Which one that I'm highlighting is the really bad part? She says the right. Okay. So I'm still here because Natalie can't type all of this. Pranav, what is the derivative right now with respect to n of ln n? You have to treat this like a chain rule, okay? Ln n. So think first of the derivative of the very outside right now, this function. What is that? You remember? If you're, yeah.
Um, I'm 100% sure, but would it just be 1 over ln n? Wait, no, ln n into n, I think. Maybe.
No, you're
Yeah.
good. It's 1 over the argument. So if you had ln of x, it would have been 1 over x. If you had ln of x squared, the derivative of the outside would have been 1 over x squared, and so on and so forth. The argument is ln of n, so you're good. But you got to do the derivative of the inside right now. What is the derivative of this guy? Again, 1 over
n.
What was that, Pranav? What was
1
that?
over n.
Yeah, okay. So you got here 1 over n times ln n. What do you have to comment about that? Any comments? You got 1 over n ln n as the derivative of ln n.
Doesn't it cancel with n ln n on the outside?
If we do a u sub, it does. So maybe we should integrate it. Because if that's such a simple u sub, you're only going to have to integrate here really 1 over the square root of u. Think about it. Now, obviously, this requires a little bit of wit, right? Like you're not going to just be walking around here and just like, bam, see that. You have to pay close attention to these steps that I'm outlining on the actual, what's it called? On the plan, on the flow chart. Now, I've taken care, because I know you guys, when you see this, you're going to be like, no, it's not integrable. I've taken precautions because I know you're going to do this. So look, if you keep going to the right, and everything fails, okay, everything fails, eventually, take another shot at the integral and comparison test, specifically this one. Because a lot of you will ignore this one. And you'll think that, nah, that seems like too bad, you know? Because let's face it, when's the last time you integrated something? Before the midterm, basically. So now your integration skills are going downhill. So you're going to be like, I don't want to integrate. I barely remember the methods now. So don't. Take the time to think if this is actually integrable, because it was. And it's such a simple integral too, once you realize the u sub you need to do. Okay, for the integral test, before we can use it, we can't get too excited. You need a couple of things. First of all, okay, so we're doing the integral test. And again, we're checking. Check. Oh my God, check for absolute convergence first. That's what I'm trying to write here. Absolute convergence. So that's what we're doing. And we're trying to use the integral test. So it's the integral test says is, let me highlight here what we're referring to. This is AN. Is AN is A sub n continuous from 3n to infinity? Yes or no? I need to know. Is it continuous? Or does it have like holes, gaps, etc.? Well, what do we think about that? Is there a value of n between 3 and infinity that will break this? Also, what I'm doing right now, I'm loading a plot. I want to show you what this looks like too. Okay, that's while you're thinking about that. I love that Desmos tried to correct me when I put the double ln in. It's like, are you sure? Are you really sure about that? I am sure, because I'm doing math 119. Okay. So I have an exclamation mark. What does it say here? Use parentheses around the argument ln. Oh, crap. There we go. Perfect. Okay, here's your function. Beautiful. Here it is. So I will show you again where n equals 3 is, if you're wondering, or x equals 3, excuse me. What do you see? What do you see? You see from 3 onwards, look, forever and ever and ever and ever to eternity, this thing decreases. It never picks back up. Okay, I can zoom out as far as you want. I mean, you can find that out by taking the limit as n goes to infinity, but forever and ever, it just continues decreasing. Okay, so, and it's also continuous. It is continuous. I mean, if you can't come up with a number here that breaks this, then you're good for the most part. You don't have to prove these. Even your prof said in one assignment that he overlooks you trying to prove these things. So I'm not gonna worry too much for you proving this, right? But the answer is yes, so we pass. Other question is, so is an monotonically decreasing? And specifically, we want it to be monotonically decreasing in between 3 and infinity. There's times, by the way, there's functions that could do this. I'm putting this in the recording too. They could do this. So you go, oh no, it's not always decreasing. Sometimes it picks up, right? And it goes back up. No. You're looking between the range for your sums, okay? Between 3 and infinity, what it does. All right, we don't care before that what it did, or after, well, there's no after infinity, but before the 3, I don't care. Okay, this doesn't exist for me. Be careful about that. So is it monotonically decreasing? Yes. How would you prove it if you had to? Who feels like taking the derivative of this? I sure don't. So how you would prove this is you would take the derivative with respect to n right now, and you would get that this thing is always, less than 0, negative. I promise. I literally promise. Like you can, again, there's some things that I can do here and some things that take so much time that I invite you to do them after in your own time if you're curious. This is one of them. The derivative here of this, I promise it will turn out to be less than 0 for all n, no matter what n you try in there. Which tells you if the slopes are always negative, your function's always decreasing. And then we go to the third one, which is the integral. We're going to take the integral from 3 to infinity of an. All right, let's go. So we have to take the integral of this. We have to square it again, ln of n. And we talked about this. We talked about the u sub that can make this work, that triggered the idea for the integral test in the first place. And we said, what if u here is ln of n? We did the derivative there, Pranav, and we got 1 over n times ln n. There we go. We're integrating with respect to dn. It'd be nice to replace dn right now, or here's what I'm going to do. I'm going to say du. I'll bring the dn up here, and I'll say du is dn over n times ln n. So in my original integral, this bit right there is du, and this bit right here is u. That's what's going on. While I'm at it, might as well change the limits. So if if n goes to 3, I plug that back in here. That's not going to be an exact number, so I apologize. Whoops. Ln of 3, and then ln of that is 0.09. U goes to 0.094. And if we plug in infinity to the substitution, we get over here infinity. There you go. So we're changing the bounds as well. Let's do it then. We've got the integral here from 0.094 to infinity du over square root of u. Square root of u in the denominator can be brought upstairs and be written like this. Okay, Natalie cannot really type this fast, so I'm going to give it to Pranav to do. Can you tell us the integral of this? What do you think?
Is it u positive u to the power of positive 1 over 2 over 3 over 2? Or sorry, over 1 over 2.
You're very close. So think of this first, Pranav, and then think about what happens if you differentiate it. The 1/2 would come down. So you want to cancel that. So you'd multiply the original by, you want to cancel that.
Yeah, okay.
So you'd multiply by 2. Okay. Take a look at what we're doing here. This is an improper integral. Might as well put in the notation and remind you that. Okay, fair enough. So next here, we evaluate. We've got the 2 is sitting outside. Limit as t goes to infinity of t, or square root of t if you want. And then minus u, again, the u here will be square root of 0.094. Perfect. Natalie, what's this limit? Without really thinking. Square root of infinity is 0. What are we thinking? Square root of a very large number. Infinity. Okay. So I don't even care about this. This is infinity, and we just failed. Okay. Diverges by integral test. Or, because we're still here, doesn't absolutely converge by integral test. Fair enough. Fair enough. Now, this guy is not an alternating series. I need to tell you that we were here. Let's follow the chart because we've gotten lost. We were here. So is AN integrable? Yes. Is it decreasing, continuous, and positive? Yes, yes, yes. For all the n being summed, yes. What is the integral? 0 or non-zero? You got infinity right now. So it's non-zero. Was the original series alternating? No. No, we didn't have a -1, remember, to the end or anything like that? No. So we actually, even though we're checking for absolute convergence, because our series is not out alternating, there's no room for us to check for conditional convergence. Basically, what I'm saying is you're checking for absolute convergence right now and conditional convergence at the same time because your series is not alternating. So that's what's going on right now. So we don't have to do an alternating series test because we failed absolute convergence. If you fail here absolute convergence, you're done. You're divergent. Done. We're not alternating. If we were, then we'd have one last chance to converge down here. But we're not alternating. So we stop here. So it's my bad. I thought there was a -1 there. And so this diverges. Done. Okay, I might have not talked about the third part here, but the third part is very easy. Is an positive or 3n infinity? Okay, and the answer is yes, obviously. Why? For n equals 3, the series is positive. Therefore, and since, again, hold on, and since an is a function, it grows, I'm going to say here, and since an grows positively with n, I have to have a little bit of room to write that, a little more. So again, for n equals 3, the series is greater than 0. And since an grows positively with n, then for n greater than 3, the series will remain positive. That's the reasoning. Okay, if you're wondering what the reasoning is when you're reading this later on, that's the reasoning. So we checked the lowest n again. We saw that it produces a positive term. And then since the function itself, the a sub n, grows positively, the terms grow positively with n, there's no way again to produce a negative term after n equals 3. It's impossible. And I mean, you can see the plot, you know, for reference at the very end. You can include the plot if you want of the function, which was this, right? All the values, you never see this dip at the negatives. You never see this increase back up. And you never see this discontinuous here between 3 and infinity. So you're good, good, and good for the integral test. Perfect. So an unexpected integration. Okay, this is what this was, an unexpected integration. And we failed it. No, I mean the test failed. We did it correctly. All right. What do you think? I got all of you to pick an example, which is awesome. And we're right on time to end this. Okay, the chart here, all it needs is to have a space here for the geometric series right around the P series area. Because again, this happens pretty rarely that we get a geometric series. And that's about it that I need to add to it. Everything else here, very good. Follow it to the T if you want to be successful and practice again these things. One comment I will make before we go, please take a moment to think about this step. I'm even going to write a hint here, like I'm going to write a note. Take a little bit of time to think about this step if this limit is easy. Because most of you, again, you are lazy and you know it. You're going to skip over this and it could have been your answer. So don't. It's better to spend a few more seconds to make sure it's not possible or it's not fruitful than to just toss it and come back after all the other questions to this. That's going to waste way more time. So be patient and think about this step, but also this one. These are the catchers. You might think it's not integrable, like the one we just did. But you fell in the trap. You have to go all the way around here. Okay, and that's not a fun trip. So take your time when you're answering these two specific questions. I'm going to make a note though on the chart. Take your time. You don't want to go immediately to the comparison tests and all the other weird stuff that we have, later on down the flow chart. You want to, if you can do it here, do it here. Because the integral test, the nice thing about it, it's conclusive. If you can integrate this function and easily, it's conclusive. If you get like a number other than 0, it goes, you diverge. Done. So if you can actually integrate and it's an easy integral, take it. Don't avoid it. Okay. So this is the intro. Again, we're going to do some of these on the next session. We're going to actually practice all of them. I want you to get good exposure on all the scenarios. We did 4 tonight, which is good. So we'll keep it up next time. And if there are no questions about it, I'll stop the recording here. Do you have any questions? All right, I guess this is a good point to stop the recording.